Welcome back, everybody. Thanks for coming to the new link. We really appreciate it. We're in Zoom instead of Teams. That may mean we have to get used to things when we're handing off and stuff. But for now, everything's going okay. Again, my name is Brad Keeler. I'm the director of the Geo-Institute, and thanks for joining us on this first of 4 Geo-Congress 2023 sneak peek live streams. What we're aiming to do, since we're going to be in Los Angeles for Geo-Congress in March, we're going to try and give you a taste of some Southern California content. Maybe not weather. I look outside, it's very cold here in the DMV. And not California-like at all, but that's okay. If you're joining us and you don't know anything about the Geo-Institute, you can head over to geoinstitute.org after the presentation is done today. Check it out. We're a technical society with about 12,000 members, most of whom are geotechnical engineers and/or geologists, and we are part of the American Society of Civil Engineers. If you like what you see today, and after all the things you fought through to be over here, I think you will. You should click like, click subscribe, click get notifications, and we will let you know every time we post something to the YouTube channel. One more thing I will say before I get it over to our introducer today is I have my friend Carl with me today, Carl Terzaghi, the father of geotechnical engineering. If you would like a Carl Terzaghi bobblehead of your very own, you can do this in these very simple steps. Head over to geoinstitute.org, click the link that says support student programs or contribute to student programs, make a donation of $96 or more to GI student programs, and you will receive your very own Carl Terzaghi bobblehead in short order. We can only ship to the US and Canada. That's the only restriction on it. But other than that, you can have your own Carl to put on a shelf. Geo-Congress, of course, coming up at the end of March. More information available at geocongress.org. Now, with all that out of the way, I'm going to hand it over to I don't know if he's the past chair already of the Los Angeles Geo-Institute chapter and program committee member for Geo-Congress 2023, Dave Albus. Thanks, Dave, for doing this today.
Thank you, Brad. I'm glad to be here. And I want to welcome everyone that's joining us and appreciate your patience while we work through those technical issues. As Brad said, I'm the principal engineer and president of Albus and Associates, and I did just recently step down as chair of the Los Angeles chapter, and I got to spend 3 years in that position, so I was very privileged for that opportunity. But now I've joined the Geo-Congress committee, and I'm excited about what we're doing there. In fact, all of us in the geo profession here in Southern California are excited to host the Geo-Congress 2023. And I know we're going to have an exciting group of speakers and panel participants. Our talks are going to cover a broad range of topics, including interesting work here in Southern California. So I highly encourage you to attend this event in March. But now I'm pleased to introduce today's speaker, Dr. Marty Hudson. Dr. Hudson is the Director of Geotechnical Engineering for the Turner Engineering Group of Turner Construction Company. And he has over 29 years of experience covering a variety of building types, sizes, and market sectors. Dr. Hudson is a licensed civil and geotechnical engineer. He obtained his BS and MS degrees from the University of California in Los Angeles and his PhD in civil engineering from the University of California, Davis. Dr. Hudson has worked as a geotechnical engineer of record on some of the largest projects in California, including the Wilshire Grand Tower, which we'll speak about today, the Ronald Reagan UCLA Medical Center, and the New Century Twin Tower development. He has extensive experience with deep excavations, shoring, soil nailing, MSC walls, ground improvement, shallow and deep foundations, including driven piles, drilled shafts, caissons, and micropiles. And he also has extensive experience with ground motion studies on many high-rise buildings, subway stations and tunnels, reservoirs, and hospital buildings. And this has included both base isolated and damp structures. He's an honorary member of the Structural Engineers Association of Southern California and serves on the Seismology Committee. Dr. Hudson also teaches courses on foundation engineering at the UCLA Henry Samueli School of Engineering and Applied Science. So today, Dr. Hudson will be speaking to us about the geotechnical challenges of the Wilshire Grand Center, which is the tallest building on the West Coast. And so now, with my privilege, I turn it over to you, Dr. Hudson.
Thanks so much. So now, getting through all of that, I again thank everyone for joining us today. And so we should be able to see my screen. Is that correct, everyone?
Yes, looks good.
Great. So thank you again for the switch of platform. So as Dave mentioned, we'll be talking about the Wilshire Grand structure. And for the first part of it, I want to introduce you to the project itself. It is a 73-story high-rise, 1,100 feet tall. So that makes it the tallest building west of Chicago and the 15th tallest building in the US. It's predominantly a hotel and office tower, both functions in the one tower. The owner is Hanjin Group, who owns Korean Airlines also. The architect is A.C. Martin. The contractor is Turner Construction. So this building was finished in 2017 at a cost of around $1.2 billion. Now, personally, I work for Turner Construction now, who built this tower, but at the time of design and construction, I was principal engineer with AMAC, who was the geotechnical consultant. So I have my feet in both companies there. So here's some more photographs of the tower. You can see on the top left, there's the plaza. There's a low-rise portion of the development on the left side of the photo. And there is the main tower to the right. So that's the entry plaza. The low-rise portion has convention and other amenities in its space. The top right shows the lobby of the hotel. So this is a sky lobby on the 70th floor. So that's the only sky lobby of a hotel in Los Angeles. And so that allows guests to really take in the views before they even check in and then go back down to their hotel room. There's a beautiful curved skylight area between the main tower and the low rise. And so there are a lot of beautiful architectural features that A.C. Martin put into it. Now, the location of the project, I'm going to start with the top picture. You can see in red, that is the tower. Now, you may say to yourself, well, it doesn't look like the tallest one. Aren't there other ones that are taller? Well, the reason for that, it's an optical illusion because the other towers are up at a higher topographic elevation. So the height isn't seen clearly depending on your vantage points. But then in the background, you see the snow-covered mountains of the San Gabriel Range in Los Angeles. So to put this in context, here's the United States. There over on the West Coast is Los Angeles. And you can see from a zoomed in geologic map, there's our site in downtown Los Angeles, west of Hollywood, Beverly Hills, Santa Monica, Malibu. And the colors on this geologic map show you where we are. The light yellow are young, recent alluvium. The darker yellow are Pleistocene age, older alluvium. And then the other colors are various types of rock formations. So you can see from that the site is right at the edge of an alluvial plain, right where some rock picks up. So that's important in what we were dealing with at the site. Here's a plot plan of the site, and you can see the streets surrounding it: Wilshire Boulevard, Figueroa Street, 7th Street, and Francisco Street. And in purple is the outline of the basement. It takes up nearly 100% of the site limits. And the basement is up to 110 feet deep. it is actually variable because the topography is sloping as we come up out of the alluvial plain into the hills there. So it's shallower in some portions, the excavation, and deeper in some portions. So as a first step, when the geotechnical investigation was being performed, we had to drill borings at the site. And with the large hotel structure that was previously there, we had the challenge of knocking holes in the structure, getting drill rigs down into the basement, and drilling with limited access equipment. That, if you do geotechnical engineering, that's a big deal to sometimes get on sites like this. And so we started getting the data out of it. On the right, you see there's an artificial fill over alluvium, and then you begin to get into the rock, which is called the Fernando Formation. Here's another boring where the rock is shallower, just a little bit of fill, but by 3 feet, you get down to the rock, the Fernando Formation. Now, there's one thing unusual I'd like you to note about this boring log, and that is the diameter of the boring. That's not a mistake. It's 24-inch diameter boring. Now, why would we drill such a large diameter test boring? The reason is because we wanted to backfill the hole with geologists, as we say in the geotechnical engineering world. That is, we wanted to send a geologist down the hole. This is Rosalind Monroe, the principal geologist on the project. And the Los Angeles Times got a kick out of this idea of drilling a hole for over 100 feet into the ground and sending somebody down to look at the soils right up close and personal. So this is a scaled drawing they made that would show Rosalind as she descended into the hole. Now, why do you do this? It's because the Fernando Formation comprises siltstone and sandstone, but there are bedding planes. So going down in person to look at them, you can see where bedding planes are, what the attitudes of the bedding plane are, the dip, and you can see the strength and even dig samples out from the side walls of the boring. So that became very important because if you have adverse bedding, it can cause instability problems with your excavation. So this is not commonly done in a lot of the world, but historically has been done in Los Angeles to some degree. Obviously, you can't do it if there's high groundwater or if there are hazards such as methane gas. So here's a geologic cross-section put together once we had the data on the site. And one of the things to note is there was a former building, which I showed a picture of previously, and that basement went down to a certain depth. And then the dashed line shows the proposed new basement. There's the greatest depth of 110 feet. And in that cross section, you can see the various formations, artificial fill, alluvial fan deposits, and then down to the sandstone and siltstone of the Fernando Formation. Now, I like to say that the Fernando Formation is a wonderful material for a high-rise building because it's soft enough to be able to relatively easily dig through, and yet firm enough to provide fantastic foundation support for the structure. So here's another picture of Rosalind as the excavation was occurring, and you can see the makeup of that siltstone material there. It also is fantastic for digging out the foundations because you could make neat cuts of the large spread footings or other foundation elements. So you see how well the siltstone retains its shape there. However, we did have one surprise on the project, and that is that we got to the middle of the site, partway down, and I got a call one day that said, we've hit some concrete. Now, I knew that we were already well into the Fernando Formation, but they said, no, somebody buried concrete. Well, that's a little bit difficult to do below the natural grade, but I came out and took a look, and sure enough, it looked like concrete. You could see aggregate and the cement binding the aggregate together, but it's not man-made concrete. It's a naturally occurring concretion. Now, you occasionally get concretions in the Fernando Formation, but at the center of the site was a blob the size of a small house. Now, we hadn't observed it in any of the borings, just had not happened to see it, nor in the shoring around the perimeter of the site. It was exactly at the middle of the site, and the bottom of this blob of concretion was above the top of excavation. So we are very fortunate in that sense. It didn't interfere with things. But here's the video. This illustrates that to get through the concretion, you had to jackhammer the material basically to break it up. And you can see the large chunks of this concretionary material that had to be removed. So this is not how the rest of the site was excavated, fortunately, but in this area, that's exactly what we had to deal with. All right, so now we get on to the design of the project. So for the design, we had to perform seismic analysis. Brandau and Johnston was the structural engineer of record, and they partnered with Thornton Tomasetti for the seismic design of the structure. And for this, they followed the guidelines of the Los Angeles Tall Building Structural Design Council. So for that, first site-specific response spectra were developed, and then were developed time series. So there was a suite of time series that were put into the structural model. So that's how the design and analysis was done from a geotechnical perspective. Now I'll move on to the shoring design. So for the shoring design, here's an example about at the deepest excavation. This is a photograph taken when the excavation had been completed. So right at the middle, this is about at 110-foot depth. And for the shoring was used soldier piles with timber lagging boards in between the soldier piles. And then in cross section, you see that the soldier piles were laterally restrained with tieback anchors. So the tieback anchors were drilled under the adjacent street with permission from the city of Los Angeles. And so as the excavation progressed, the tieback anchors were drilled and locked off at the design load. So that's how the shoring was accomplished for the most part. However, on one of the sides, the street was very narrow on Francisco Street. And in fact, across that narrow street was another high-rise with a basement. So you were restrained laterally how wide the tiebacks could go into the ground. That made it difficult to support the entire soil mass. In this case, the solution that was obtained was to remove a portion of the retained soil. Now, this is not something that we usually do, to remove a portion of the street, but by doing that, removing that wedge, it reduced the weight enough of the retained soil that we got a sufficient factor of safety. So fortunately, the city of Los Angeles agreed to evacuating temporarily half of the street so the excavation could be made and vehicle traffic could still go on the other half of the street. So the city of Los Angeles did give permission for that. On the other side of the site, we had another problem, which is the Metro Red Line, now called B and D line. They have their tunnels under the street. Now, those tunnels were in operation during the entire construction. So here's another view as excavation had occurred to show you where the tunnels were under the adjacent street. And then in cross section, you can see how close the closer tunnel was to the basement excavation. In fact, it was as close as roughly 5 to 7 feet away from the proposed new basement wall. So that's very close to it. So then the question is, how do you retain the excavation on that side? Now, as with a lot of developments, we had to retain every inch of basement excavation, so you couldn't simply reduce the width of the basement on that side. Rather, we had to retain it. So here's a cross section of the solution that was obtained. Now, this supportive excavation system was designed by Safali and Associates, and then it was constructed by Malcolm Drilling. So here we see another complexity for the shoring on that side. In blue, it shows the depth of the former basement. Remember, the basement went partway down that was previously there. So first, soldier piles were drilled outside of the former basement and tied back as excavation and demolition of the basement occurred. Then, once that former basement was completely demolished, then an inboard line of soldier piles could be drilled that were independent and not structurally connected to the upper row of soldier beams. So there's your second row of soldier beams. Then here's a tieback anchor, but then below that depth, below that initial tieback for the lower soldier piles, there became a problem. And that is, if you tried to put a tieback here, you might run into the tunnels. So instead, we switched to raker braces at the lower elevation, since we couldn't put the tieback anchors at that elevation. Now, rakers are a problem because they're in the site, which makes construction of the new basement more difficult, and they require temporary footings for the rakers. So that has to be coordinated with the permanent building foundations. So that's the design. And here's a photograph of what it looked like after it was implemented. You see with this dashed line, that's the break between the upper outboard soldier piles and inboard soldier piles with its tieback anchor heads that you can see there. And then here's the rakers and the raker footing. And then here's another problem with rakers is that you need to be able to construct the basement wall. So here you have one raker for every 2 soldier beams, which required a whaler beam to transfer the raker load into the soldier piles. But the whaler had to be offset away from the soldier pile with these standoffs. And the standoffs then could allow for the basement wall to be constructed behind the whalers. So that's a lot of steel and a lot of detail work in order to construct that. So as you can imagine, first the whaler, rakers, raker footings are constructed, and the soil was left with right below that raker level. Then once all of that is in and preloaded, then the final excavation of that wedge of soil could be made. So there's just a lot of complexity to that. and it's a lot of detail work. Then after the final basement was constructed, then the rakers could be carefully cut and fished out from the multiple levels of the basement. And then finally, there were slabs with windows in them that had to be backfilled with slabs in the holes after the rakers were removed. So it's just a lot of detail work in order to accomplish that. Now that's the design and the construction, but Metro, rightly so, wanted to assure that the tunnel would not be damaged and that there would be no disruption to subway service during construction. So before this was constructed, we had to analyze and prove that the tunnel would perform acceptably, and then monitor the tunnel. So that required a large team. This is the team just with the task of evaluating and approving the shoring next to the subway tunnel. On the left side are AMAC, the geotechnical consultant, and all of their sub-consultants on the evaluation and instrumentation side to make this work, including Jacobs Associates, which is now McMillan Jacobs, JL Patterson, Sol Data for monitoring, Digitex for vibration monitoring, and Comet Electric for installation of wiring and data transmission out of the tunnel. Then on the ownership side was Martin Project Management and then Turner Construction for tunnel entry and coordinating installation. Under Turner was Cefali and Associates and Somas, and then the structural designer. Then Metro for the review and approval of all of this, including Matthew Crowe, Sam Mayman, John Jaramillo, and Parsons Brinkerhoff was hired, which is now part of WSP, to review that the analysis and design of the shoring was adequate. So the first step was to look at the existing condition of the tunnel with photographic surveys all along the tunnel. Then next was the finite element evaluation of the staged shoring and excavation to see how deformations occur and how stresses change within the tunnel liner and how that would affect the tunnel itself. Now, along with that, a careful analysis of the tunnel liner and the concrete and steel within the tunnel liner, that was done by Jacobs Associates. And what you have to understand after this analysis is we found in our analysis that the tunnel would move up and toward the excavation. Now you might think, why would the tunnel move up? The reason is because with that large volume of earth being excavated, that causes a heave of the entire excavation. And that heave doesn't end just right at the shoring. The heave continues on beyond the project because the Boussinesque bulb continues well past the limits of the project. So that causes an uplift in all of the ground and therefore a tunnel heave. And if you think about the tunnel, then that means we're creating a new hill within the tunnel so that now after the excavation, the trains would go up over a small hill that didn't exist before because of the heave from the excavation. So that with that type of deformation upward, and then plus the lateral deformation due to the shoring itself, then we had to say with the tracks moving up and over, would that cause the passengers on the trains to experience discomfort? Would they feel this new hill and this sideways motion? Would it cause people to fall down on the train or have to grab the bars going around this new feature from the deformation? So J.L. Patterson did that evaluation of train movements occurring over the deformed track. And they found that it would not cause discomfort to the passengers, nor would it cause excessive wear on the wheels. So all of that is very unusual for a geotechnical evaluation, right? But it's all consequences of geotechnical considerations, and that is the excavation and shoring for the project. So now, once the analysis showed that things would perform acceptably, then it's time to monitor, because monitoring program is more important than any analysis, because you have to check to see, is it performing as we expect it to? So there were two main portions. That is monitoring that occurs outside the tunnels, that is on the shoring itself and on the street. So on the shoring itself consisted of sloping clinometers, tieback anchor load cells, raker strain gauges, and then street survey monitoring and soldier pile monitoring. So that's exterior to the tunnel. And then finally, interior to the tunnel, using automated total stations, accelerometers to check vibration impacts on the tunnel, and then installing prisms all around the interior of the tunnel that the automated total station would shoot to. So here's a picture during our installation. We could only do this at, say, 2 in the morning when the trains weren't running, and then drilling into the side of the lining and installing brackets and reflectors. So from this photograph, you can see the flash from my camera on the reflectors around the perimeter of the tunnel that were just installed. And then here's the completed installation. Here's the automated total station, and then the conduits we had to install to get the data out and the power into the automated total station. And then the mounting of the reflectors all around the tunnel. Now, again, this isn't something I normally thought I would be drilling into the lining of a tunnel as a geotechnical engineer. But hey, it was fun, and Metro wanted us to do that. So sure, I'll get up at 2 in the morning and install reflectors if that's part of the project. So once all of that is installed, then we come up with a set of monitoring criteria, because anybody can install monitoring instrumentation, but the most important thing is to have eyes on the data and to know what to look for as the data is coming out. So on this table, each row is a different piece of monitoring equipment. And then we developed 3 types of action levels. We called it threshold, response, and shutdown. So shutdown means stop construction. It's moving too much or vibrating too much. But threshold just means carefully evaluate. So things worked really well, and we never got to a shutdown value. We got to about the levels that we were considering in the evaluation. So here's a sample of the monitoring website that Sol Data put together, taking data from all of these different sources, including manual surveying. And then we could see, so here's a graph. In this particular case, you see in the tunnel, as the tunnel is rising while excavation occurs, and you could see that it got to our anticipated level, which we called the response level, and stayed just below that. So that was exciting and fun, but it was very satisfying to see that the predictions worked very well. Then periodically, we put together detailed monitoring reports that showed how everything was responding and our evaluation of that. You want some kind of a summary with a one-page piece of text that everyone can look at and understand. So some of the data was very interesting, such as the rakers. The rakers every day had higher than lower stress, higher than lower stress. You had to separate out that daily fluctuation with long-term trends. Now, why did you have daily fluctuations? It's when the sun would hit the steel, causing expansion and higher stress on the shoring. So that causes continuous small movements in the shoring due to the sun hitting the rakers. Here's data on the streets, and yes, we saw the street rise on the ground surface away from the excavation. Then it dropped a little bit right next to the excavation to the shoring movement, and then lateral movement outboard from the street toward the excavation as one got right next to it. You can see the movement, the street coming up, and then it settled down. Now, vibration monitoring worked very well. You could see the vibration whenever a train went by. This was an acceleration from the train on the tunnel lining of 0.006 G. So during soldier pile installation, how much vibration? Well, that's 0.007 G. So almost identical to train passage vibration. And we could see then other vibration from train passage. Then we were fortunate enough to have an earthquake because this is Los Angeles. And I can say it would be very fortunate for us all if during Geo-Congress we had a nice earthquake, not enough to cause death, but to be interesting for everyone there in Los Angeles. But I can't promise an earthquake, we can only hope. But in any event, during the excavation, we had an earthquake and it had 0.017 G. So that was about double the acceleration that we saw from construction or train passage. So none of that caused any damage. Hey, let's talk briefly about the foundations. The main tower was supported on a mat foundation bearing directly on the siltstone. Then the low-rise portion was on spread footings. So you can see the mat foundation is only a portion of the site. So how was that evaluated? Well, you can imagine with a standard mat foundation, if you have a concentric load, we can evaluate that fairly well. But here's a complexity to add. You had a very stiff basement wall on one side of the foundation that effectively stiffens and prevents curvature of the mat on one side. And then in addition, you have excavation on one side of the mat, but not the other. So all of those factors, soil structure interaction, interplay. So the reasonable approach for this, in this case, was to perform a 3D finite element soil structural evaluation. So this is the model that we built, including the mat foundation, the excavation, the basement walls, and the shear walls at the core of the building. So how did those all interplay? We then finally got the settlement contours to find out what the settlement would be. And you can see it's off center because of the fact of the wall stiffening one side and the excavation being on the other side. So from this, we could evaluate the differential settlement between the mat and the footings and between footings. So at the end of the day, there's the big pour, and it was made as a single continuous pour of concrete over a weekend. And at that time, It was the largest continuous placement of concrete in human history. So I got to meet the Guinness Book of World Records person who came out to document this event. And so it was a big deal when that occurred. So there's the placement of the concrete over the 3 days. And you can see there's little white features here. And then there's white boxes you can see at the edge. Those are a big cooling plant because the heat of hydration of the concrete was so great that we had to cool the mat for weeks afterwards to prevent the temperature from becoming excessive in the concrete mat. So that's something you have to think about when you have very great thicknesses of concrete. So here's a video of the excavation and the beginning of placement of concrete. So that was the former building, carefully disassembled, excavated, and there's the excavation occurring down to the bottom. Then the mat foundation, the rebar being placed. There's the concrete. Then there goes the core of the tower. And so then the core was coming up from that. This was a concrete first, and then steel came up second on the perimeter. So with that, conclude my talk, and let's see if we have time for any questions.
Thank you, Marty. If I had an applause button, I would push it right now and we could hear everybody clap for you. What a fascinating project, and I'm envious that you got to do that. All those various challenges, it's crazy, absolutely crazy. Yeah, so for our viewers, if you're interested in submitting a question, please do. And while you contemplate all that information that Marty just provided, I personally have a couple things I would love to throw to you, to Marty, maybe to kind of kick it off. So you talked about some key things there. Obviously, the elastic properties of the Fernando Formation became a really important aspect of your analyses, and I'm curious to know how you went about, assigning those properties to that formation. I know it's not hard rock, that we don't have hard rock here for the most part in California. It's stiff soil.
Right. Yeah, that's a great question. So for evaluating that, what the elastic properties of the siltstone and sandstone are, we took samples with thick-walled samplers. And I know that a lot of people worry about disturbance from the thick-walled samplers, but in California, that's pretty standard practice to use them. And the thick-walled samplers, driven samplers, do take pretty good samples of this type of material. So we took samples and then did odometer testing in the laboratory. And on the rebound, you can get the stiffness of the material, and did a number of those tests. So that was one thing to do, was odometer testing from relatively undisturbed samples, perhaps you could call it. But then in addition, we had shear wave velocities to try to correlate, because you want to validate what's happening. And then thirdly, we did back calculation from performance of an adjacent high-rise, and with a finite element two-dimensional analysis, we looked at what the shoring did during movement in the Fernando Formation and looked at if those properties described well. So using a validation for an adjacent structure. Now, all of those three things did cross-reference quite well. The rebound from the odometer test, the shear wave velocity degraded to get what you would expect, plus the validation back calculation. And so at the end of the day, the deformations we measured were very close. For a geotechnical engineer, it really surprised me how close they were. We predicted around 3 inches of settlement of the mat, and it was about 2.5 to 3 inches of settlement. And the rebound and the movement of the subway tunnel all were very close to the estimates. So that all goes back, you're right, to the properties, the elastic properties of the Fernando Formation bedrock. So, but I would never want to rely on only one thing, like a couple of tests. I would want to cross-check and cross-validate.
That's phenomenal. In our business, getting that kind of accuracy between our model and the reality is that's unusual. So well done. And I know, having worked with you on these kinds of things, putting together the models, the analytical 3D models is no simple task itself. There's lots of places in there that can challenge that part. So that's great. The second thing that I had was you had a picture early on that showed the geologic structure of the Fernando Formation there in one of the cuts. And it looked like you had, I assume, bedding planes that were dipping out of slope into the excavation. So I was kind of curious to know how you handled that versus what appeared to be earth pressure evaluations following more of a typical Rankine earth pressure angle of 60-30. Did you study the effects of the adverse geology that must have been there in some of those cuts?
Yeah, and that's very important because, as I mentioned, you could otherwise potentially get a failure because those bedding planes could conceivably be a softer clay stone layer within it. So based upon the evaluation and as you saw a picture of our geologist, Rosalind Monroe, the city of Los Angeles asked that during excavation that our geologists look at the sides the whole way down to check if we missed any localized bedding area. So you see that it's very important, but we found almost all of it was massive. There were not a lot of bedding planes, and the bedding planes in this particular spot did not exhibit weakness. So we did have higher pressure on one side than the other based upon the unfavorable direction.
Oh, yeah.
So that's how we dealt with it, but careful observation is required. I call it after the Peck observational method. You can do all of your testing and analysis you want, but during construction, it's important to validate while you go to make sure you're on the right track.
Absolutely. One of our viewers, Sin Hu, has wanted to know if you were dealing with issues of encountering the previous tiebacks from the old basement work. Was that a problematic thing?
Yeah, that's a great question. The old building there was so old that it did not have tiebacks. Okay, it had been built. I forget what we had concluded about the temporary shoulder, but from across the street, they had used tiebacks. We may have occasionally hit an old tieback with a new tieback, but then you can move over or core through it. So we did that occasionally. And then in one case, as we're pumping grout in a new tieback, it emerged in an unusual location, we think following the path of sand tieback backfill from across the street. So it didn't result in damage, but we found the grout found an unusual path through an old tieback.
It does that, doesn't it?
We used to backfill them with sand in the old days. Now they use grout.
Very good. Yeah, you always can count on those kinds of issues to show up and have to deal with them. Another one of our viewers, Ian Gidley, was interested in two things. What generally was your K-knot that you developed in the Fernando Formation? And also, did you have a concern of the risk of a shear band developing in that material during the unloading condition? And I assume that could have happened particularly along your predefined bedding planes.
Yeah, that's great. Is interesting for the K value. We did design the shoring assuming a KA condition, an active earth condition. Now that's fairly standard practice for Southern California, and it's still a little bit on the conservative side. But we assume that with the deformations of an order of 1 to 2 inches at the top of those very tall soldier piles, that's sufficient to get you close to active. And so then we had the measurements from the rakers and the tiebacks, which corroborated that. So we did get close to active conditions. So that saves a lot of money on shoring design. So so I know I'm not directly answering your question. What was K0? Well, whatever it was, we relieved it. But then we designed for K0 for the permanent basement wall. But here's the interesting thing. If we relieved it during the shoring, then we could go with a traditional, normally consolidated K0, because at worst, it would back up to there. It wouldn't go back to its pre-existing K0. So that also made the design of the basement walls more economical. So then at the end of the day, what was K0? Well, it was probably significant because these are over-consolidated materials. So it wouldn't have been a normally consolidated, it would be an over-consolidated K0. But whatever it was, it's no longer that.
I got to give you credit that you convinced the city of LA to allow you to use an active pressure. That hasn't been my experience with them. Okay. Well, I don't see any new questions coming through, and I don't want to be a hog, but Marty, I think that this was a very fascinating project, and obviously you spent a lot of hours cranking numbers and considering a lot of things there. So hats off to you, to a job well done.
Thank you.
And yeah, Brad, I'm not seeing anything.
No, I think that's it. You guys got to everything. Thank you so much to our viewers for asking questions. We always appreciate that. It's always a little nerve-wracking. We think, uh-oh, nobody's going to ask anything. So we do appreciate it when you come through in the end. And really, that enhances the experience for everybody. So thanks, Marty, for a great presentation, getting us kicked off in this live stream series for our preview of Geo-Congress 2023. Sorry again to all our viewers and to Marty and Dave for running you around and making you do a little extra work this afternoon. But we persevered and we made it. So again, for our viewers, if you liked what you saw, and it was a great presentation, so you better have liked what you saw, click like, subscribe, get notifications, and we, of course, will let you know every time we post something to the YouTube channel. We will have 3 more of these live streams, one in December, one in January, one in February. So be watching out for those. We will let all of you know when it's coming your way and what it's going to be about. Registration for Geo-Congress 2023 will open between now and the next live stream in December, so be on the lookout for that as well. We would love to see all of you in Los Angeles. I did wear my fancy Geo-Congress 23 hat today. I didn't show that off at the beginning. I will do that now. We are going for the sleazy 80s Los Angeles theme while we are at Geo-Congress. So that's something for everybody to look forward to. Thank you for watching. We have a lot more great stuff coming up on Geo-Institute YouTube channel, so be sure to check that out, and we will see